In this video, we will be discussing a few reactions of phenols, alkylbenzenes, and benzyl ethers. These are some reactions that happen in and around a benzene ring that are sort of special standalone reactions. In the next chapter, we will be learning a lot more about reactions that happen on benzene rings. But let's get started with this topic today. The first reaction we'll discuss, actually the first three reactions, are all reactions of phenols, which, as you remember, are compounds with a benzene ring having at least one OH group attached. The main property of phenols, or one of the main properties of phenols, is that they are acidic, and so they react with bases like hydroxide to form the conjugate base of the phenol, which is sometimes referred to as a phenoxide. Phenoxide corresponding to alkoxide for alcohols. Now, phenols are much more acidic than alcohols, so hydroxide essentially converts phenols 100% into the phenoxide form, but weaker bases do not, like bicarbonate, would not appreciably remove an H+ from a phenol. Other stronger bases would, so sodium amide, Grignard reagents, acetylides, sodium cyanide, all would be very strong bases and all would form the phenoxide from phenols. Pretty standard reaction. The next reaction is definitely not a standard reaction. It's one that produces a useful product, and this is called the Kolbe carbonation, and essentially it adds carbon dioxide to the molecule, and so you get a carboxylate from it. It's catalyzed by hydroxide. In fact, it requires a full equivalent of hydroxide, so it's not really catalyzed. Notice that what happens is that the carbon next to the OH ends up gaining the CO2 negative group, replacing a hydrogen that was at that position. It's not shown in the polygon type figure, but you know that there's a hydrogen. Okay, we will be learning the mechanism of this reaction. Also, you should note that it has a big star next to it because it is a carbon-carbon bond making reaction. Now, this product, of course, if you start with phenol itself, could be treated with dilute acid to produce the corresponding carboxylic acid, which we have learned would be called orthohydroxybenzoic acid. You should, though, also realize that that compound is called salicylic acid, and it's the basis for aspirin. So this is a reaction that's done a lot in industry to produce salicylic acid. Also notice in this reaction that if there are other groups attached on the ring at various positions, the reaction will still occur as long as there's at least one ortho carbon available for substitution. In other words, you can't have both orthocarbons be substituted with other groups. In that case, then there would be no reaction. In this slide, I'm showing you the mechanism of the carbonation, the Kolbe carbonation. First step, the hydroxide simply pulls off an H+ from the phenol, as we learned in the previous reaction, to produce a phenoxide. And then this comes the interesting step in which the carbon-carbon bond making reaction occurs. Notice that what happens is a pair of electrons comes out of the benzene ring and attaches to the carbon dioxide, produces the carboxylate, and a pair of electrons moves down from the oxygen to form a carbon-oxygen double bond. This is then the keto form of an enolate, which you can get to by simply taking the H+ off of the benzene ring and putting it back onto the oxygen and shifting the double bond down. That is essentially keto-enol tautomerism, and you have learned that the keto form generally predominates in a keto-enol tautomerism, but in this case, the enol form predominates. So the final product is back to being a phenol, which is in essence an enol. If you look carefully, you'll see there's a carbon-carbon double bond with an OH group on it, so it looks like an enol. So why is the enol form more stable than the keto form in this case? And the answer is because the enol form is aromatic, and we know that aromatic rings are particularly stable, and therefore the driving force in this direction is to reform the aromatic ring. I've also shown you on this slide the curved arrows for the second step. That is the key step in the mechanism in which the carbon-carbon bond gets formed. Notice I've drawn a curved arrow from the negative charge on the oxygen into the position between the carbon and the oxygen. That produces the double bond on that position, moving a pair of electrons out of the benzene ring into the space between the carbon dioxide carbon and the benzene ring carbon. and at the same time moving a pair of electrons out of one of the double bonds of the CO2 and to form a negative charge on that oxygen. Okay, let's move on to the next slide. This is a new reaction, another reaction of phenols, and it looks kind of familiar to you. Essentially what we're doing is turning a single bond OH into a double bond O. But that, as we've seen, is really not an oxidation. That's just an enol formation. But notice that in this reaction, when you react a phenol with Jones reagent, you not only get a double bond O on one side of the molecule, you also get a double bond O on the exact opposite side, the para position. And you shift the electrons around in the ring and you form what's called a quinone. We've seen quinones before in the previous group of slides because we learned the name hydroquinone, in which you have two OH groups on the para position of a benzene ring. Well, this is a reaction in which phenol itself gets oxidized to form quinone. Now it's unusual because you are starting with one oxygen attached to the benzene ring and you're ending up with two oxygens attached to the benzene ring. Question you might ask is, where does the second oxygen come from? And the fact is it comes directly from the Jones reagent itself. This is a redox reaction, and it's one that we won't learn a mechanism for, nor will we even write a balanced equation for it, although you could do that by following the steps that we've learned before for writing balanced equations of redox reactions. It's a fairly complicated equation. But just learn that phenols get oxidized to quinones by Jones reagent. Now you may question, what happens if there's already a group at the position para to the OH group? Like, let's say there was a bromine or a, let's say, a methyl group at this position. And the answer is then no reaction occurs. You have to have that position open in other words, with just a hydrogen on it, in order for the oxidation of phenols to form quinones. Here's another new reaction. This is reactions of alkylbenzenes. Actually, it's not a new reaction because you have learned this reaction in a previous chapter. Any kind of R group, and notice that that R group could be a methyl group, in which case it just gets oxidized directly to carboxylic acid, or it could be a longer chain with 2 carbons, say an ethyl group, or 3 carbons, a propyl group, or 100 carbons even. And the fact is that the KMNO4 seems to be chewing the side chain down, spitting out carbon dioxide for each of the other carbons until it gets to the last carbon, the one attached to the benzene ring, and that is then oxidized to a carboxylic acid carbon. So it's a degradation in the sense that you are breaking carbon-carbon bonds in most cases. But it is a useful reaction in that it's one of the good ways of putting a carboxylic acid group onto a benzene ring if you already have a carbon group on there. Question arises, what happens if you have other groups on the benzene ring? Well, other groups like nitros or halogens or other carboxylic acid groups, a variety of things don't get affected. But if there are groups, then they also get oxidized to carboxylic acid groups. Here's another very useful reaction, one that we will be learning about, not so much because the reaction itself is useful, as because it serves as the basis for it's called a protecting group. Notice that what we're doing in this case is taking an benzyl ether, so we have to start with a benzene ring and a CH2 and then an OR group. So it's an ether because the oxygen has 2 carbon groups attached to it. Neither one of them has a double bond O, so it's not an ester, it's an ether. And interestingly enough, for whatever reason, when you treat a benzyl ether with hydrogen gas, notice that's the element hydrogen, not water, but the element hydrogen, and hydrogenation catalyst. We've learned about hydrogenations before, particularly with double and triple bonds, but in this case it's an ether. So this is quite unusual. What happens is the OR group from the ether gets split away, and the CH2 of the benzyl ether becomes a CH3 group, which means that you end up with toluene as a product. Remember, toluene is the special name for a benzene ring with a methyl group. Well, it turns out in this case that the toluene is generally not the desired product, and it's going to be washed away in the workup. But the important product in this case is the alcohol that also gets produced. That is the RO group with the hydrogen, and the hydrogen having come from the H2 catalyst. So the byproduct in this case is the toluene. The main product is an alcohol. Now you might ask, why would we want to make an alcohol in this weird way by decomposing an ether? Here's why. Turns out that the benzyl group can act as a protecting group for alcohols. So let's say we have an alcohol that we're starting with. This is an example of a synthesis using the hydrogenation of benzyl ethers in the synthesis. Notice in this case I've started with a compound that has both an alcohol and a halogen in the same molecule, and I've reacted that alcohol with benzyl chloride, that is the benzene ring, the CH2 and the chlorine, and pyridine. There is serving to soak up the excess HCl byproduct that would be formed. In any case, what we're producing is an ether, so the OH group from the original alcohol picks up the benzyl group from the benzyl chloride and becomes a benzyl ether. Now the OH group is masked in a sense. For example, we could now make this into a Grignard reagent and react it with any number of things that Grignards react with. In this case, I've chosen acetaldehyde to react the Grignard with, and then followed by H+, as we always do in Grignard reactions. And we would end up with, as you would expect for a Grignard, an alcohol. So we have a new alcohol formed. Now if we do the hydrogenation of the benzyl ether, it removes the benzyl group. Toluene goes away as a byproduct, and we end up with the OH group. This OH group that we originally had in the molecule reformed. So in essence, we're making this molecule into a Grignard and adding the CH3CHOH onto it. But you remember that you can't do that normally with Grignards if there's an OH somewhere else in the molecule. So what we've done is we've masked the OH by putting a benzyl group onto it. Then we did the Grignard reaction here, and then we unmasked it, or what's called deprotecting it, taking the benzyl group back off again using this new reaction that we've just learned, the hydrogenation of benzyl ethers. So you can see that that reaction is useful as a way of removing a protected group from an alcohol. There are many, many, many other protected groups for all sorts of functionality that you will find in molecules incompatible with other reactions that you might want to do elsewhere in the molecule. And so what you do is you protect the group that you don't want to be there in such a way that you can easily then return it back to its original form. This is simply an example of that. But this, just to remind you, is the new reaction that we're learning in this case. That's the end of the presentation. Thank you.